Hi, Professor Math here. Welcome back for another exciting video involving our radical expressions. Today we'll be talking and discussing how to perform different operations with these radical expressions. From the basic idea of simplifying things that are non-perfect radicals to more advanced concepts like adding radicals together, multiplying them, dividing them, things of that nature. So first off, we have the square root of 32x to the 8th. Now, in a previous video, we discussed how to simplify them when they were perfect. So, when they're non-perfect, because the square root of 32 is not a perfect square, we need to do something a little different. So, if we ignore the variable for a second, the square root of 32, again, we're looking for the biggest perfect square that goes into 32. Well, biggest perfect square would be 16. And 16 times 2 is 32. That's why this would be the same thing as 4 square root of 2. So we start off by doing that. And then for the exponents, well, if we remember from our previous video, we're always dividing the exponent by the root of the radical. So since the exponent is 8, the root is a 2. Divide 8 by 2 and we get a 4. Since I worked into it nicely, that's all we had left over there. So then we'll have 4x to the 4th square root of 2 is our final answer. The other rules for the variables still apply, so if it's an even root and we have an odd exponent coming out of it, we still need to remember to include our absolute value symbol with the expressions. So we'll also discuss what happens if the exponent isn't perfect and divides into it nicely as well. So with this example, we have the 4th root of 16, a to the 24th, b to the 13th. Well, this one's kind of nice because the 4th root of 16 is perfect. It's just simply 2. And then for both a and b, well, for a, 24 divided by 4 is exactly 6. So we can take a to the 6th out. It's an even exponent, so we don't need to worry about the absolute value. But when we do the b value, 13 divided by 4, 4 does not go into it nicely. So what you need to do is, don't think of it as a decimal, you think of it as the remainder then. 4 goes into 13 3 times, with a remainder of 1. That's going to be like 3 1/4. This is important because we need to write this as b cubed. And then the remainder 1 tells us there is 1 b left over. So that would be the 4th root of b. There's no other numbers left inside because 16 was a perfect 4th. A to the 24th is a perfect 4th as well, so there's no a inside. But the b had a remainder of 1, so that's why there's 1 b left over. Had the remainder been 2, then there'd be 2 b's left over. It'd be a b squared. If the remainder was 3, then there'd be 3 b's left over and it'd be a b cubed. Now, we still need to remember to include the absolute value sign because it was an even root and we had an odd exponent that came out of that. So our final answer would be 2a to the 6 and then the absolute value of b cubed and then the 4th root of b. So for this one now we're going to apply all those together. So we have the cube root of 81. 81 is not a perfect cube. It is a perfect square, but it's not a perfect cube. So again, we need to go through the process of, okay, what perfect cube goes into 81? Well, we can go through that, and we can think of this then as the cube root of 27 times the cube root of 3. So that'll tell us it'll be 3 cube root of 3 left over. It's perfectly fine. Another way, and probably a more beneficial way to look at this for future problems, is to recognize that 81 is 3 to the 4th power. Well, if we divide the exponent by 3, it's 4 divided by 3 is 1 with a remainder of 1. So this would be the same thing as, again, 3 to the 1st, and then the cube root of 3. Because, again, similar with the variables, whatever is the whole number comes out, whatever is the remainder stays inside. And now with our variables, well, we have the cube root of y to the 12th. 12 divided by 3 is 4, so it's just y to the 4th. It's perfect. Whereas the cube root of z to the 7th, well, 7 divided by 3 is 2, so it'll be z squared, with a remainder of 1, so it'll be the cube root of z. So for each one of these, we have a 3, a y to the 4th, and a z squared on the outside. And on the inside, we have the cube root of 3z. The 3 and the z are what's left over. There's no y's left over because it was perfect, but the 81 and the z to the 7th are not perfect cubes, so that's why there's stuff left over in there. Again, it's a cube root, so it's an odd root, so there's no absolute value, so that is our final answer. So again, the key is just simply going through and simplifying each one of the numbers individually. You can think of them as looking for perfect squares or cubes or fourths for the numbers, or you can rewrite them as an exponent and then go from there. It's entirely up to you which way you want to see it. The exponent notation is very useful for what we're going to talk about next. Well, not this next one right here, but the following one. So the square root of 12, well, that is square root of 4 times square root of 3. So it's 2 radical 3. The square root of c to the 6th is c cubed. It was an even root, odd exponent, so we're going to have to include the absolute value. And then the square root of d to the 3rd, well, is d square root of d. Because 3 divided by 2 is 1 with a remainder of 1. And again, d to the 1st is an odd exponent, so it should be an absolute value. So the proper way to write this answer would be 2 times the absolute value of c cubed times the absolute value of d times the square root of 3d. C cubed and d should both have separate absolute value signs to account for the possibility that one of them might be negative, the other one is positive, so there's no need to keep them together in the same one. Technically, you probably could put them right in the same one. Now I'm thinking about it. I'm just thinking more ahead for your homework assignments. When looking at the solutions, they'll be a separate absolute value sign. So you can probably write them as one, but they will be separate for your solutions. All right, so that's the idea behind simplifying a radical when it's non-perfect, no matter what the roots are. Now, the idea of rationalizing the denominator. So this is occurring, like with our complex number I, which we discussed in the previous units. We cannot have a radical in the denominator. If we do, we have to get rid of it by what we call rationalizing it. To rationalize the denominator, we need to multiply top and bottom, numerator and denominator, by some quantity, some sort of radical, so that radical now becomes an exact root, becomes a perfect root. And that looks like this. So if the denominator was just a square root, we just simply multiply by the square root again. Because multiplying the square root times itself will create a perfect square, and the radical will go away. So the example they use is 2 over radical 3. Well, you multiply top and bottom by the radical 3. Top becomes 2 radical 3. The bottom, radical 3 and radical 3 become radical 9, which is 3. And that's great. However, if it's any other root, if it's a cube, fourth, fifth root, or so on, multiplying just by the radical is not enough to make it perfect. Example right here, if we have the cube root of 2, if I only multiply by the cube root of 2, I would get the cube root of 4. And that's not a perfect cube. So what they suggest is, thinking back to in terms of the powers, which is why I had you write them like that in the previous examples, if we have b to the x power, we need whatever is left over to make it a perfect exponent to match up nice. So since 2 is raised to the first power, that's why the rationalization requires you to do 2 squared. Because 2 times 2 squared becomes 2 cubed, and that's now a perfect cube, so the radical goes away. So don't always just do by the inside for a cube root or a fourth root or so on. Identify what is necessary to then make it perfect. So you could have problems where the radical is in the fraction form like this. Just simply rewrite it as the square root of x to the 6th divided by the square root of y to the 7th. Before going through the rationalization process, always simplify as far as possible. The top becomes the absolute value of x cubed, because it's a even root with an odd exponent. The bottom becomes y cubed times the square root of y. And the y cubed should also be an absolute value. So actually, what I'm going to suggest is similar to what I've been noticing on the homework and textbook problems. Don't worry about absolute value for these kind of problems. Okay, so ignore the absolute value aspect. It honestly makes the problem too complex. So we're just going to assume at this point all variables are positives. If you're just simplifying a single radical expression, include the absolute value sign. Pretty much follow the directions. So if we have the square root of y in the bottom, all we need is to multiply top and bottom by the square root of y. Up top becomes x cubed square root of y. On the bottom, the square roots cancel, leaving a y. Y times y cubed is y to the 4th. So we have x cubed square root of y over y to the 4th. That would be our simplest answer now. Again, we're assuming all the answers are positive, so that's why we're going to ignore the absolute value signs. If we have this one, we have the 4th root of 6 divided by the 4th root of 5x. So the 4th root of 6 can't do anything with that. 6 is not a perfect fourth, and there's no numbers inside there that become a perfect fourth. And same thing with the 5x in the bottom. So to rationalize, I'm not going to multiply by the 4th root of 5x. That's not enough, because 5 times 5 is 25, and that's not a perfect fourth. So we need to recognize that we have only one 5 in the bottom. To make it a perfect fourth, I need 3 more. We only have one x in the bottom. To make that a perfect fourth, I need 3 more. So we're multiplying top and bottom by the 4th root of 5 cubed x cubed. Because now on the bottom, we'll have the 4th root of 5 to the 4th, x to the 4th, and on top we'll have the 4th root of 6 times 5 cubed, x cubed. So when we multiply up top, 5 cubed is 125. That times 6 will give us 750. So it'll be the 4th root of 750, x cubed. And on the bottom, well, since they're both perfect fourths, we just have 5x left over. And that would be our simplest form of the answer. Again, we need to make sure that if it's a 4th root, we need to include 4 of each type. We only have one 5, that's why we need 3 more, that's where the 5 to the 3rd comes from. We have one x, so we need 3 more, that's where the x cubed is coming from. Alright, same idea is happening here. We have the 5th root of 3. Divided by, well, we should rethink of 4 as an exponent, which says 2 squared. So it'd be the 5th root of 2 squared y cubed. So again, to rationalize, we need to make sure we have a perfect fifth. Well, we currently have 2 2's, so I need 3 more. Same thing with the y. We currently have 3 y's, so I need 2 more. So we're going to multiply top and bottom by the 5th root of 2 cubed y squared. Because with 2 2's, I need 3 more. That will now make that a perfect fifth, so we'll have 2 in the bottom. Since we have 3 y's, we need 2 more. That'll make it a perfect fifth. That's why it's y in the bottom. And then up top, it'll be the 5th root. Well, 2 cubed is 8. 8 times 3 is 24. And then y squared. Alright, so that's the idea of rationalizing it with a cube root, a 4th root, 5th root, or square root in its bottom, whatever it is. Again, you need to make sure it's a perfect radical to do that. Please make sure you talk to me if you're having some issues understanding where the 2 cubed y squared or whatever else we used in previous problems is coming from. Now, in general, simplifying radicals, we always need to make sure it's in the simplest form, meaning the index, the root is the smallest as possible. There's nothing inside the radical, which is called the radicand, that are factors for the nth powers. There's no fractions, there's no radicals in the denominator. So if we're multiplying 2 radicals, they really need to be the same root. If we're doing a cube root times a square root, while there are ways to simplify that, it's more complex and outside the scope of this particular class. So what we'll do is, we're going to multiply the outside numbers first. So 5 times 3 is 15. Then we're going to multiply the inside numbers. Negative 12 and 18 becomes a negative, let's see, what is that? Negative 12 times 18, I think that's a negative 216. Yes, negative 216. And then a times a squared is a cubed. B to the 4th times b to the squared is b to the 6th. Well, we're lucky in this case because negative 216 is a perfect cube. It'll be negative 6. A cubed is a perfect cube. It'll just be a. B to the 6th is a perfect cube. It would be b squared. So you can multiply all of them together and get negative 90 ab squared. So that's the value in this one. Now, obviously, not all of them will be perfect radicals, but the idea is still, once we multiply them, we now have a problem very similar to the very beginning first 4 examples of this video, and we go through the simplifying process from there. Just again, one side, since we are multiplying 2 radicals, again, don't worry about the absolute value. Only do that when it's a single radical, and the directions say account for the absolute value. So here we're multiplying 2 square roots. So again, still multiply the outsides. 6 and 4 is 24. The insides, a and 2 is 16. C to the 4th and c is c to the 5th. D to the 5th and d cubed is d to the 8th. So the 16 is a perfect square. That would be a 4. C to the 5th is not, so if we divide 5 by 2, it would be c squared with a 1 remainder, so there will be a c left over. D to the 8th is a perfect square, so it will be d to the 4th. So our final answer will be 96, 24 times 4, c squared d to the fourth, and then times the square root of c. We can have negatives on the outside. That's perfectly fine. The key is just make sure there's no negatives inside an even root. We're allowed to have it inside an odd root. That's fine, but not inside an even root. So multiply on the outside, we'll get a negative 6. And then it's the fourth root of on the inside. 8 and 4 is 32. X cubed and x to the 7th is x to the 10th. Y squared and y to the 5th is y to the 7th. Now, for the fourth root of 32, that's going to actually equal 2 times the fourth root of 2. Because 32 would be 2 to the 5th power. So if we do 5 divided by 4, we have 1. That's why it's 2 to the first on the outside. And a remainder of 1, that's why there's a single 2 on the inside. So it'll be negative 6, and then 2. We have the fourth root of 2 left over. We then take a look at the x. 10 divided by 4 is 2, so it'll be x squared. With a remainder of 2, so it's an x squared on the inside. And then for y, 7 divided by 4 is a 1, so it'll be y on the outside. With a remainder of 3, that's why it'll be y cubed on the inside. So we multiply the negative 6 with that, we'll get negative 12, x squared, y, and then the fourth root of 2x squared, y cubed. So just again, as we were going through each one of those, make sure you are multiplying the coefficients on the outside and everything on the inside together. And then just remember how to go through simplifying the numbers and then the variables themselves. Just again, don't stress over the absolute values. Now, for adding or subtracting radicals, they have to have two things in common. First off, the radical has to have the same index, it has to be the same root, and it has to have the same inside with it. They have to be like terms, essentially. So we can't combine a square root and a cube root. We can't combine like the square root of 2 and the square root of 3. Because while they're both square roots, their insides are different. So only combine them when they're the same on the insides. So for both of these, we have to simplify the radical first. So the square root of 98, well, 98 is 49 times 2. So this will be 7 square root of 2 minus 32 is 16 and 2. So it'll be 4 radical 2 for the square root of 32. Don't lose the 2 on the outside, that outside coefficient. Because then it becomes 7 radical 2 minus 8 radical 2, which is just then negative radical 2. So you have to make sure you account for the outside coefficients. After you simplify the radical, make sure you multiply with it. They both have square roots. They're both 2's on the inside. That's why you can do 7 minus 8 to get the negative 1 on the outside of our radical 2. For here, square root of 8 is 4 and 2. So this will become 4 and then 2 square root of 2 plus 3 and then 50 is 25 and 2. So it'll be 3 times 5 square root of 2. So this will tell us 8 square root of 2 plus 15 square root of 2, which is 23 square root of 2. Still the same inside, still radical 2. That's just more because I was thinking of simple numbers to work with. They're not always radical 2's, don't expect that. But again, they're both radical 2's, that's why we can add the 8 and 15 to get the 23. It's similar to saying 8x plus 15x, you say 23x. Whereas if it was like 8x plus 15y, can't combine them. Now we don't have to have just 2 radicals. There could be 3, there could be 4, there could be so many more than that. It still comes down to simplifying each radical as far as possible, and then combining the like ones. So 12 is 4 and 3. So I can think this is 5 times 2 radical 3, plus 27 is 9 and 3. So plus 2 times 3 radical 3. And then 128 is 64 and 2. So minus 8 square root of 2. So we get 10 radical 3 plus 6 radical 3 minus 8 square root of 2. Well, the radical 3's can combine. 10 plus 6 is 16. Radical 3. The radical 2 can't combine with that, so it stays separate as minus 8 radical 2. Unlike the polynomial functions, there's no particular order you have to write the radicals in. So if you choose to write cube root and then, square root of 3 and then square root of 2, fine. If you want to put it in like an increasing order, so from least to greatest, you can write as negative 8 radical 2 plus 16 radical 3. Same answer, not going to be the biggest deal. Now, when we're talking about multiplying radicals, we're talking about the idea of foiling radicals. So we're going to be multiplying two binomial expressions. So you still go through the FOIL process like you would for any variable. The only difference is these would be radicals inside here. And then once you're done multiplying, then simplify as far as possible. So we have this expression. We do the first terms. We'll get 12 square root of 6. The outer terms, minus 24 radical 3. The inner, we'll get plus 15 radical 4. And then the last, we'll get minus 30 radical 2. Well, can't do anything with square root of 6, so it says 12 square root of 6. Can't do anything with radical 3, so it says minus 24 radical 3. Square root of 4 is 2, so this will become a 30. And we can't do anything with the square root of 2, so it's minus 30 square root of 2. So again, there's not too much going on there after the actual FOIL process. If each one of those radicals could have been simplified, then you need to make sure you go through and actually simplify each individual radical. The only one that could was the square root of 4, and that was just a perfect one, so there's nothing we had to worry about there. Alright, so for this one right here, we have same idea. Still want to go through the foiling process. This example should look very similar to stuff we've already done, though, so you should be anticipating what's going to happen right here. So we multiply our first terms. We get 49 square root of 4. Our outer terms, we'll get plus 21 radical 6. Our inner terms, we get minus 21 radical 6. And then our last terms, we get minus 9 square root of 9. Well, the square root of 4 is 2. So 49 times 2 is 98. 21 radical 6's, one's positive, one's negative, so they cancel. And then radical 9 is 3, so 9 times 3 is 27, so it's minus 27. And then since there's no radicals left, we can actually subtract that, and we get 71. So this should look very similar to when we talked about the conjugates of our imaginary numbers, because that's what this is right here. So in addition to finding conjugates of imaginaries, we can find conjugates of radical expressions as well. It's the same idea. Everything is the exact same, we just change the middle sign only. So if that was, for example, negative 7 radical 2, we would leave it as negative 7 radical 2. We only change the middle from negative to positive or positive to negative. Alright, apologize for the length of the video. That was much longer than most of them are, but there was a lot going on here. A lot of different individual examples you had to see, rather than making like 7 separate videos that we just put into one big one. Alright, so that's our operations with radical expressions. Again, I appreciate you watching, and Smith Math is out.